is atomic structure. And I like doing this now. This is the atoms focused or atoms first approach. A lot of chemistry textbooks would now go into like chemical reactions and species, then go into stoichiometry right away. I like doing this first because it explains a lot of that stuff. It explains why sodium and chlorine form sodium chloride, because you'll learn about the electrons and the structure and the bonding and all of that. So this followed by chapter 4 and 5 on the next exam really gives you a good handle on that. So here are our learning goals. Mathematically, at the very beginning, you'll need to be able to convert between wavelength, frequency, and energy and interpret that in context with the electromagnetic spectrum. So this is something I'll introduce pretty early on. Explain the photoelectric effect, which is Einstein's Nobel Prize work. A lot of people think he won for relativity. No, he won for photoelectric effect. Never won for relativity. Relate energies absorbed by atoms to electronic transitions. That's going to be coming from Bohr's work. Effectively assign quantum numbers to describe orbitals. Write electron configuration. So when we get the two most important things that come out of this chapter for chemists, if you will, is writing electron configurations and understanding how the periodic table structure can be explained based on quantum theory. So a good chunk of your exam will be this, and the rest will be the quantum theory development. So this is the electromagnetic spectrum. And some people just call it light in general, but of course there's visible light as part of it. What is electromagnetic radiation? What is it? Light. That's not defining it. What's light then? Who's saying that? Where's that come from? Energy. Okay. It's propagation of energy. When you think about anything in the electromagnetic spectrum, it's energy propagating through space. Okay, what's unique about, and it travels as a wave. And what's unique about electromagnetic waves is they don't need a medium to propagate. Okay, to hear sound, you have to have a medium to carry the sound. That's why there's no sound out in space. If the spaceship explodes and you're outside the spaceship, there's no sound. There's no way for the sound to travel. It has to have a medium. Now, if you're in the ship that's got an artificial atmosphere, of course, then you would hear explosions and the sounds in there, of course. Electromagnetic radiation doesn't need a medium to propagate. So our sun is shining out there, right? And giving off the entire electromagnetic spectrum. Now, it certainly has areas that it gives off more than others, but it basically generates the entire electromagnetic spectrum. Not all of that reaches us, of course. But it's traveling through space, which is effectively a vacuum, okay? And the difference in these electromagnetic waves is what? What's the difference between microwaves and X-rays? Andrew? Their wavelength is one thing. What else? Their frequency. And the other one? What? Yeah, amplitude varies too. There's another one though that I'm thinking of. Amplitude is the height of the wave, basically. No, they all travel at the speed of light, so that doesn't vary. The energy, right? We said the photon energy, right? Yes, the energy of the waves, right? That comes from Planck's equation. The frequency is related to the energy. So on this particular spectrum here, you see down here is the shortest wavelength and therefore the highest energy. So you see things that you know, hey, X-rays, ultraviolet, that stuff is dangerous, right? High energy. You got to protect yourself from that. At the other end, stuff that's not nearly as energetic, low energy, you got stuff like radio waves and microwaves. Visible somewhere in the middle. Okay, I say middle, but visible. And you got right there's the visible spectrum running from violet to red, right? And right next to violet is ultraviolet, and right next to red is infrared. That's a good way to remember it, of course. And violet is more energetic and shorter wavelength than red, right? And the visible spectrum runs from about 400 to 750. There's no discrete beginning and ends to these things, just a rough idea, okay? It's tough to say exactly, hey, yeah, 400 is visible, 399 is not, or what about 399.9, So we just give a rough idea of the ranges based on energy. And you're all familiar with microwaves, so we can create microwaves in your kitchen, right? With a magnet and electricity and spinning magnet that creates the microwave that basically rotates the water molecules in your food and heats it up. That's why you always have to have a little water in there to get it to work good. Radio waves, don't get confused, don't have sound themselves. What you do is you put the sound wave and modulate the sound wave with the radio wave. It carries it. You tune in, whatever station I was listening to, NPR this morning, so 90.3, and I've got all these other frequencies coming in, and I match the one I want, maximum energy transfer. That's the idea, that I'm picking up all the other frequencies are there. I'm just matching it, and then what they do is they separate out that sound wave. That's what your amplifier is doing from the radio wave, and that's what drives your speakers and all of that. So don't think that radio waves have sound. So this is a way of looking at waves here. And wavelength and frequency are inversely related. You see that over here too, right? Down here is the longest wavelength. It's also the smallest frequency. What? Oh, there's frequency. 10 to the 4th, right? So, and here you're over 10 to the 24th. Super high frequency down there. That's the high energy short wavelength. So effectively, B is shorter than A, right? Wavelength can be measured anywhere on the same point of the wave, of the corresponding wave. So you can measure it from trough to trough or start to start, like that. So a complete wave, if you will, would be that. And if you think about two people holding a rope, and if I take the rope and go like this really fast, high frequency, right? High energy. The ends of the rope don't move, right? And the rope, the matter of the rope doesn't move from me to the person holding it over there, right? Just the energy that propagates through the wave. Okay? The only difference is that electromagnetic waves don't need a medium to propagate. They work with corresponding, and this was Maxwell's work, electric and magnetic fields propagating off of each other like this. And this is kind of what figure 3.2 is telling you. You don't need to know that, but that's just the way it's, described in terms of the way it can propagate. Now, there's the speed of light, and the units we're going to want it in, meters per second rather than miles per second. Think about that speed, 186,000 miles per second. Okay, pretty darn fast. There's the equation that relates speed of light to wavelength and frequency. So you'll have speed of light in meters per second, wavelength in meters. That means frequency has to be 1/seconds, right? Units have to work out. So that's a hertz if you're into sound and music, anything like that. Same thing we do in sound, right? You got your, in the old days when I was a bit of an audiophile, I used to have a graphic equalizer, 10-band graphic equalizer. They're not around anymore. I still have an old one, but you got all your frequencies on there. And those are, if you will, oscillations per second. Okay. It's just the units metric wise are just going to be per second. Okay, but it's really like oscillations per second. So that's how your units work out. And of course, you can rearrange that equation and solve it any way you want. Question? Lambda is the wavelength. Nu is the frequency. And c is the speed of light. Kind of like a cursive V, but there's a Greek letters. Anything else? So once again, on the left, high frequency, short wavelength, high energy. On the right, long wavelength, low energy, low frequency. Okay, so over time, scientists were looking at different things. They would develop, had these spectroscopes they had developed, and you could look at sunlight and things like this. And as they started to look closer and closer with better and better spectroscopes, they realized the light coming from the sun wasn't a continuous spectrum, but contained a bunch of these little black lines. Okay. And you can read about all the different scientists, Fraunhofer and Balmer and Rydberg in your book, and a little bit the history. I'm not going to go through that too much. I'm going to mention a few things, then I'm going to jump into Bohr. But they noticed that there wasn't really a continuous spectrum. These little black lines. And then they also realized that when we could look at two different things, both in absorption and emission spectrum. So I guess I should draw something here. So imagine a tube of hydrogen gas. And let's say I basically put a voltage through there. High energy, I'll just describe it like this, as a, I don't know, high energy voltage going in there. The hydrogen gets excited and it absorbs some of that energy. Well, I guess I could say not a voltage. I guess I want to use like a laser. Okay, so light. It'll absorb some of that energy. That's an absorption spectra. So instead, so I'm shining something like a full spectrum of light through it, but the hydrogen's absorbing certain wavelengths of energy. So you see an absorption spectrum. Okay. In emission, trying to think of a better way to draw this, but so effectively the lines they're seeing here are because the gas molecules in the region around the sun or in the corona of the sun are absorbing certain wavelengths of light before they reach our eyes in our spectroscope. Okay, that's an absorption. So instead of seeing a continuous spectrum, we're seeing black bands where these different gases in the corona of the sun have absorbed it. Okay, that's a better way of doing it. My figure wasn't that great. So now imagine I take a tube of hydrogen and I excite the hydrogen. Let's get rid of this. Take a tube of hydrogen and excite the hydrogen with some sort of voltage. And when it kind of goes from an excited state and relaxes, similar to what you do when you get home after listening to my lectures, and kind of pass that on the couch, relaxes, and it gives off energy, right? The energy it gives off is exactly the same as the energy that it would absorb for an absorption spectrum. So if I excite hydrogen, it absorbs energy and then it emits it, right? The wavelengths at which it emits are exactly the same as the wavelengths it would absorb if it was in the corona of the sun, right? They correspond to each other, which makes sense. Well, it makes sense to me now because I know where we're going, but it will make sense, hopefully. So this is one of the big kind of things that they were uncovering and starting to realize that classical physics couldn't describe this and explain it. The bright lines in emission spectra and the dark lines in absorption spectra of elements correspond to each other. So this is a debate every year, just completely eliminating this, not talking about it at all. One of the things this is referred to as ultraviolet catastrophe. Let's just keep this simple. One of the things that classical physics couldn't do was basically explain this drop off or the fact that this changes with temperature. They just had no models to describe this. It's the idea if I was to take my fire poker, my fire pit, stick it in there and heat it up. Okay, this is what you see. It glows different colors based on its temperature. And you reach a certain point where that emission intensity drops off. And this is what's called the ultraviolet catastrophe because it happens after the ultraviolet region. Your book doesn't describe it much too. And to be honest with you, if you take physics, I guess, I'll go into it a little bit more maybe. I personally don't even have a great understanding of the ultraviolet catastrophe. Every time I go teach this stuff, I read it over and over and try to put together a little bit better explanation, but I never been able to come up with something. So don't kill yourself over this. Just accept the fact that classical physics cannot describe what happens when we heat up what's called these, perfect black body radiators. And I'll leave it at that. So Planck comes along. He's kind of the first of the quantum scientists that are going to win the Nobel Prize and also begin the idea of quantum theory. And to explain this ultraviolet catastrophe and some of these other things we were seeing here, he proposes that objects emit electromagnetic radiation or electromagnetic energy in integral multiples of an elementary unit or quantum. So the idea is that it's quantized in nature. What we mean by this is not something new, is that that's photoelectric effect better in terms of quantum theory, but I struggle with this stuff. I mean, things being quantized is not new at this point. It happens all the time in nature. I think I might have mentioned this in my video. Piano keys, right? Or biology. You give birth to 1 dog, 2 dogs, not 2.5 dogs. You walk up steps. You have enough energy to get up to the next step, or you don't. There's no in between, right? So this is the idea that he's thinking about to explain some of this stuff. And the idea is that matter doesn't, like classical physics would have said that if I got matter, okay, and I shine electromagnetic radiation on it, it will keep absorbing and absorbing and absorbing and absorbing and increasing in temperature, increasing in temperature, and increasing temperature. Planck comes along and says, no, based on what we're seeing here, that's not what's happening. There's these kind of steps in which it absorbs and emits. And it absorbs and emits the same. And then it needs, if you will, enough energy to absorb the next step and emit that step. Rather than what classical physics would say, there were no steps. It would be an inclined plane. If it's got enough energy here, it absorbs a little bit more and then emits that. It doesn't work that way, Planck is saying. So the idea is that you can, put, if you will, multiples of this right here, which is Planck's constant, which we now is defined as an actual number based on frequency and energy of the electromagnetic radiation. And there's the constant. There'll be multiples of that, whole number of multiples, which means you have these kind of discrete packets of energy, 1 times this, 2 times this, 3 times this, right? Classical physics would have said, well, there's an infinite number of energies between 1 and 2. There's 1 point, right? Everything between 1 and 2. And Planck is saying that's not the case. So now what he's saying is the energy is related to the frequency, of course, which is also related to the wavelength. This is getting at photons, which we don't know about yet, and we're not going to really talk about yet until Einstein comes along. But the idea is that the frequency of light is going to have these little packets of energy, right? Each of these photons is going to have the energy of that particular wavelength of light. Okay, that's a lot, and I didn't exactly go through it smoothly. So, do some reading. This is one chapter, which reading will help, but I'll quote you Richard Feynman, so you don't get frustrated. I won't quote you, I'll paraphrase. I won't quote him. He's famous for saying no one understands quantum theory, and he was being totally serious. He said, and he compared it to relativity. He said, a lot of people understand relativity. He said maybe at one time only one guy understood it, but eventually everybody understood it. He said no one understands quantum theory. And the reason is because there's no analogies in nature. It's unique. It doesn't behave like a ball on a string or a planet revolving around the sun or anything like that. It does weird things. And I'll explain some to you as we go on. They won't make sense to you. How can that be? How can the electron be here at 1 minute, 1 second, and over here at another second, but not travel from here to there? How can 2 electrons being thousands, hundreds of thousand miles apart be intertwined in their spins? That if I have an electron in Switzerland that's coupled to an electron in Murfreesboro, and one of them changes spin, the other one will change spin correspondingly, instantaneously, with no change in time. How's that possible? Well, it's not based on what we know, but that's what happens. We have experiments, we do this stuff all the time now. And this is a little bit of the ideas behind some sort of encryption techniques and quantum computers and all of that. So he's famous for saying, don't try to compare it to something. I'll do that because as humans, we have that vain desire to understand things in certain ways, but just to help you through a little bit. But he's famous for saying, don't try to compare it to something, just accept it. And the reason we know it works is because all the math works and all the predictions work. That's the science that works. But don't try to, compare it all the time to something. All right, let's do a basic calculation, something more mundane. And we'll need calculators out because I didn't solve this or anything. What is the energy of a photon of light from the largest quantum dot? The one with the wavelength from the 640 nanometers, straight from your book, was the energy of 1 mole of those photons. Okay, so right off the bat, we see energy of a photon. Let me explain this right here. This is the energy of a single photon. That's what this equation tells you. Okay, the energy of a single photon. That's why the number will be really small. Okay, so that's a single photon of light with that particular frequency. So we know we're going to use that equation. And we know we're going to get this, right? That's going to allow us to get the frequency because we're starting with a wavelength. Okay. And we've got our constants. We know Planck's constant. We know the speed of light. So let's solve this equation right here for frequency, and then put it into here, right? And get our energy. right? That's all. So let's take this first equation and we'll say 3.0 times 10 to the 8th meters per second is equal to 640 times 10 to the 9 meters times my frequency. And I need someone to solve that for me. 3 times 10 to the 8th divided by 640 times 10. Remember to use 640 second EE negative 9, not times 10 hat. We'll run into problems because that'll be order of operations. It's one of those examples I told you. It'll divide by the 640, right? That's what it'll do. It'll treat it as two different numbers. But if you do 640 second EE negative 9, it will treat it as a single number. And what do we get for the frequency? Anybody? Second EE8 divided, 3 second EE8 divided by 640 second EE negative 9. 4.7 times 10 to the 14th. That'll be seconds to the minus 1 or hertz. Thank you very much. That looks right to me. Got confirmation from anyone? Yes, thank you. Okay, couple confirmation. So that's my hertz or seconds to the minus 1 frequency. Now I can just put it in here. E is equal to, let's look up what H is, 6.626 times 10 to the minus 34. Notice the units, joules seconds times my 4.7 times 10 to the 14th seconds to the minus 1. My seconds will cancel out nicely, and I'll be left with joules. And what do I get for that? Thank you. With joules, it looks right. Exponent wise, should be right around. Whoops, that's a 19, not a 9. Joules. But the question, that's the energy of one photon. And a mole, well, we can just use Avogadro's number. So that's joules per photon times 6.02 times 10 to the 23rd photons in 1 mole. And we should get like what? 23rd and 19. It'd be like 4, like 18 times 10 to the 4 or 1.8 times 10 to the 5, something like that. Thank you. 1.9 times 10 to the 5. Didn't really pay attention to sig figs. The 640 really is only 2 sig figs, so we're good. 1.9 times 10 to the 5, and that is joules per mole. That's all. Just use those 2 equations. Well, you can do it in 1 step, of course. Just substitute the 1 equation into the other and do it in 1 step, and it becomes, right here. We could have just done that, right? But the first time I do it, I like to do it like this. And everybody sees each step, but you can certainly do it in 1 step. Questions? Yes. Yes. -9. No, it's -34 and 14. So, yeah, so that's got to be -19. Yeah. Yeah.
So where'd you get the 3.0 times 10 to the 8?
Oh, that's the speed of light. So that's a constant that's given to you, right? It'll be on your constant sheet right there. I use 3.0 instead of 2.998. Yeah, I just use 3.0. That's fine for most of your calculations in this class. Photons refers to anything. Number. That's why I would say number of particles. Could be photons, could be ions, could be atoms, everything. That's anytime you have a mole, doesn't matter what a mole of whatever you want. Could be eggs, right? Be a lot of eggs, but okay. Anything else on this calculation? Now this is the stuff I really like. The photoelectric effect. So this is Einstein's work. So what we had observed was that electrons were emitted from the metal surface when illuminated by, what is that? Is that a sentence? Electrons are emitted from a metal surface when it is illuminated by, and absorbed, yes. When it's illuminated by and absorbs electromagnetic radiation that exceeds the threshold frequency. So what classical physics had observed was that certain metals will emit electrons when electromagnetic radiation is shined on them. Okay, and certain metals would and certain wouldn't, and different types of electromagnetic radiation were used. Now Einstein has the work of Planck here, and these ideas to start to study this and explain it. And this is not something you'll find in your book. So this is, my additional slide. I don't even think it's in your slides. So what you see here on the y-axis of this graph is the current, which is the number of ejected electrons. Okay, when you think about current, okay, it's flow of electrons, if you will, the number of electrons in that kind of stream. Okay, and then on the x-axis you have energy, increasing energy. And this is something classical physics would have never predicted. Classical physics would have said I can take a metal, shine electromagnetic radiation on it, and if I get an intense enough radiation, eventually the electron will jump and move. No, that's not what happens. Okay, your model's no good if it doesn't describe some empirical evidence, all the empirical evidence. So what Einstein was showing was that basically there's some threshold frequency that has to be reached. It makes sense when you think about it from a quantized nature, just like the steps, right? It's kind of like having a nail in a board, right? And you're sitting there because you're really tired or lazy and you're going like this to the nail on the board. And the nail's not moving, right? Doesn't matter how many times you hit the nail. If you don't use enough energy to move the nail into the wood, it's never going to get in, right? Doesn't matter how many times you hit it. There's some minimal amount of energy that's necessary to get the nail moving. Same thing. That's what Einstein's saying, is that there's that threshold. That threshold, if you will, is the frequency, which is the energy. You equate those two. You have to think of those two as synonyms. When I say high frequency, I mean high energy. When I say we need a higher frequency, that means we need more energy. Okay, so, what's the other part of that graph? It didn't show up. Okay, I can draw it in. If the lambda is greater than the threshold, now remember, wavelength and frequency, everything's up there if you want to take a picture. There's no more to show up on that slide. Wavelength and frequency are inversely proportional. So this says, if wavelength is greater than the threshold, the energy is too low, there's no electron emission. That's down here, right? I can reword that to say, if frequency is less than the threshold, the energy is too low, right? Those two statements are synonymous. If the wavelength is too high or the frequency is too low, the frequency is less than the threshold, the wavelength is higher than the threshold, the energy is too low, and there's no electron emission. This is the idea where quantum theory comes in now. This is not what classical physics would have predicted. Higher intensity does not cause electron emission if the energy is less than the threshold. So intensity would look like this. Higher intensity, let me draw a red line. This was supposed to be on here, just didn't show up. Would look like this. How would it look? Right? So it's not exactly right. So let me redo that because it has to be. More like that. That would be higher intensity. Same threshold. So higher intensity means more photons, more density of photons. Okay? Which means I can get more electrons flowing. Because Einstein described it like this. I'll come back to this. Light is quantized, behaves like a stream of massless particles. Now he's taking what Planck said is that the matter is quantized, the electrons are quantized. Einstein's saying light is quantized, behaves like a stream of massless particles. So now he's saying that light has particle characteristics. Classical physics, light is a wave, it diffracts, it reflects, it diffracts. That's what characterizes a wave. Okay? Einstein's coming along and say, well, actually, light has particle characteristics. Okay? Imagine photons, think of them as balls, hitting electrons embedded in glue. If the energy of the ball is low, it can't eject an electron. If it exceeds the strength of the glue, electron is released. Higher intensity equals more photons or balls. If the energy is greater than threshold, more balls eject more electrons. Why? Well, each ball can hit an electron. Think it like that, right? Each photon now can hit an electron. So it's quantized in the sense that you have this minimum energy level that's going to do this. That's what this is here. Different metals having different wavelengths. You see that? So which one of those metals requires the least energy to get a photon moving? You fell into the trap. You caught your own mistake. Carter caught it as he said it. No, the one with the I said least energy, so that means the one with the longest wavelength, right? Which means the lowest frequency, therefore the lowest energy. So cesium requires, of those four metals up there, the least amount of energy to get an electron moving. But these are the thresholds, if you will, for different metals. Questions? The earlier quantum stuff's a little bit difficult to digest. Some of the ultraviolet catastrophe, understanding some of Planck's work, if you start reading more about that stuff. Photoelectric effect is digestible. Much more digestible. So now, further work's going to go along, and people are going to start looking at these. What we call these are called line spectra. So remember, this is an emission spectra, and this is hydrogen here. And remember, this is hydrogen getting excited, and then it releases these particular bands of energy. Okay, these particular wavelengths. And this is one of the scientists I told you can read about all the different scientists kind of worked up to Bohr with these atomic spectra and stuff like that. And this is an empirical equation. What does that mean to you? Empirical equation. If I say something's an empirical equation, what's that mean? Means it's just based on data. There's no theory behind it. He has no idea why that equation works, but it works to describe those four lines. And you can read, I think N1 has to be greater than N2 and so forth. And there's another equation that's talked about that's similar to this one in the book, or maybe it's, I can't remember if it's in your book or not, because I often read different sources. But they're all empirical equations trying to describe these lines. and there was another one, I didn't include that slide. That's why you see the word more general empirical equation. I deleted that one. I didn't need to feel like I included it. But moving on then, so you can't explain why the equation describes the lines. That's why Bohr's work comes over. Bohr, another Nobel Prize winner. He's going to basically kind of take the work that came before him and explain it in terms of the structure of an atom and the planetary model that you're all familiar with electron orbits around the nucleus, right? In the Bohr model, the electron of the hydrogen atom revolves around the nucleus in a series of concentric orbits, each of which represents an allowed energy level. So this is the idea of this quantized nature, okay? There isn't the plum pudding model where electrons are just swirling around the nucleus, free to go wherever they want. They're confined. Now, obviously, hydrogen only has one electron, okay? But that electron can exist in different energy levels. So Bohr's work is specifically, working on the hydrogen atom. And he describes the energy, and he comes up with this constant, and it's related to whatever energy level it's in, whichever orbit's it in. And this is what's confusing too. They're done as negatives. So the larger the negative number, the less energy it is. And they become less and less negative, closer to zero, if you will, as you go out from the nucleus. So if you imagine putting in a 2 here instead of a 1, that's times a quarter instead of times 1, and put a 3, that's the idea. It's going to get less and less negative, right? So a large negative number means low energy. And they did this. There's a good reason they did it. It's just, it has to do with, ionization energies and removing an electron from an atom. That needs to be a positive energy. So realize there's no such thing as negative energies. It's just a kind of a way of notating it. There's no such thing as negative energy, right? So except for in maybe like human beings giving off negative, people that are really negative energy. But there's nothing like that in physics. There's no such thing as a negative energy. So it's really just, it's almost like kind of a directional thing, the way velocity has a direction, something like that. So that this equation now describes the energy of each of these orbits, but not only that, he takes it further. And where's that equation? Well, I don't even have it written here. It's the equation on your outline. This one here. He takes it further, and now we can describe changes in energy as it moves between these energy levels. The electron, okay? The different ends, okay? The constant is still there, and it's just F means final and I means initial. So it's really not much of a change from the equation you just saw in the PowerPoint slides, right? You're just making it a change in energy now between energy levels. And now what we're seeing is this, and this is the brilliant part of his work, is that he's able to exactly describe where these energy lines come from that we were seeing all along in all these spectroscopes, these things, right? But this equation predicts the wavelength, but has no idea why it predicts it or where that's coming from. Bohr comes along, and what he's able to do is to describe all of these kinds of transitions. And that's what this is. And I wish I had that equation here. I can write it, but it's easy just to go here. The transitions between any of these energy levels, and initial and final, okay, and tell you what the amount of energy is, and then you know what the frequency is from Planck's equation, and then you know what the wavelength is. So electron transitions occur when an electron moves between two energy levels. The ground state, n equals 1, so this is the ground state, closest to the nucleus. Is the most stable, lowest energy state of a particle. An excited state is any energy state above the ground state. Now, if you put into this equation these particular transitions from 3 to 2, 4 to 2, 5 to 2, and 6 to 2. Oops, I covered the colors there. I did that. Whoa. Oh, what did I do? Any of those transitions into this equation, you'll get the energy, right? And then you can calculate the frequency, right? Just like we did. Then you can calculate the wavelength. You will get wavelengths that correspond to these 4 bands. That's what this is here. Red, green, blue, and purple, they correspond to these 4 bands. It's not really green there. This is not the best picture, but well, I don't know. Yeah, I don't know how accurate the arrows are. I forget what they're. You might be doing this in lab. I forget if we're still doing this lab or not. I think you are. You actually look at the hydrogen spectrum through a spectroscope. So you'll not necessarily have agreement of color sometimes. But the key is to calculate the wavelength, and then you can describe basically the wavelength. You should get one around 4. What is that? 1, 2, 3, 4. So 420. So maybe one around 410, one around 430, one around 490, and one around 650. Now, should make sense to you. The red one is this one here. Why do we know that's the red one? From 3 to 2. Who said that? Carter said, because it's the lowest energy. That transition should be the lowest energy. It's going from, just like dropping a ball, right? What's going to have more energy? Dropping it from the top of the steps or from 2 steps up, right? So the lowest energy should be the red one, right? Because red is less energetic than violet. So this corresponds perfectly to these transitions. So 3 to 2 gives you that first band there. Right over here, this red one. And then the next one, the 4 to 2. So this is the 3 to 2, 4 to 2, 5 to 2, and 6 to 2. Transitions described perfectly by the Bohr equation. That's the emission spectra you're seeing. You're seeing electronic transitions within the hydrogen atom. Now, keep in mind, when you do this in the lab, you're going to have a whole tube filled with hydrogen. So there's going to be a mole of hydrogen in there. I'm just guessing. I don't know how much is in there, but you know what I mean. There's going to be tons of hydrogen atoms. So there's all sorts of transitions going on. These are going on also, and these, but you can't see those. They're not in the visible range. One's in the ultraviolet, one's in the infrared. We can't see those with our eyes, right? Certain animals can see infrared, right? Nocturnal animals, we can't see infrared. We can put on special goggles to see infrared, but it's not, our eyes are not sensitive to that. They evolved to see visible light, which is obvious why, because we live under a big blanket of visible light from the sun. Questions? So there's all these transitions going on. And those visible ones you're seeing, that's just a group of hydrogens that are, been excited up to n equals 3 and come back down to n equals 2, and you see red.
It's going from like 6 to 2 or even 3 to 2 that was in that red spectrum on the.
This one?
Yeah. So that's the the lesser one. So it would be like 6.
No, 6 to 2 would be the highest energy one because it's falling the most steps. So that would be the highest energy is on this end of the spectrum, violet. This is in nanometers, so this is wavelength. So they're inversely proportional. So the lower wavelength has a higher energy. So this is the higher energy up here, high E, and this is low E. Right? That makes sense? So those transitions, the 6 to 2, that's what it means. That's why the line is purple. Go with that, just go with those two. That's the purple one all the way over here. And then the red one. The other two colors are a little bit off. The green one's definitely off. And that's going to be, I just did that one. And the red one's going to be this one right here. Okay. So the electrons absorb, get excited, and then when they come back down, they emit this energy. So let's do a calculation. What are we doing on time? Let's do a calculation. What is the change? This one I've got worked out. I mean, it's just a slide given to me, so it's already got it solved. What is the change in energy associated with the electron transition from n equals 4 to 2? So effectively, we're doing this one, right? 4 to 2, that green one is what we're doing. So we can go ahead and calculate the wavelength just for the heck of it. But all they're asking for, what is the change in energy associated with the electron transition from n equals 4 to n equals 2? Well, we're going to use that Bohr equation. It's on your outline, right? And the initial is 4 and the final is 2. That's all there is to it. Use that constant that comes with the equation. I might have changed it from the one in the book. I can't remember. I think I changed. The one in the book was a different transition. So I just wanted to give you something different. That's why I got rid of the actual practice number. One in your book, I think, is 3 to 2 or 5 to 2. Don't worry about all the work function stuff, by the way, that your book goes through. Yeah, 3 to 2. Is what your book does. Okay, so we're going to put the 2 in the final there, right? It'll be 2 squared or 4 squared. And we get a negative energy, of course. Now I want to calculate the wavelength. We take that energy. We're going to need to do this. I don't have it worked out. But we'll calculate the wavelength and go back and look at our electromagnetic spectrum and see where it is exactly. So is everybody okay with calculating this? Now the negative means it's an emission. It's going from higher to lower. If this had been the reverse, and just do it yourself mathematically, if it had been 1 over 4 squared minus 1 over 2 squared, you would get, so that would be, you get a negative number in the parentheses, right? And therefore you get a positive number, which means it's an absorption. So the sign is just absorption and emission. The magnitude of the number will not change. It'll be the same, 4.084 times 10 to the minus 19 joules. So the negative and positive is just like a directional. It's negative if it's emission, positive if it's absorption. And if it absorbs enough energy to leave the hydrogen atom, we call that ionization. Okay? And you can actually calculate that, how much energy to completely ionize the electron from the hydrogen atom. So your final there is just infinity. You don't have to calculate that. Yes?
So energy is made from the entire atom, not the electron.
Well, it's the electron that's transitioning and therefore emitting the energy in photons. Yeah. But that's part of the atom. So the atom, it is the electron transition that's emitting the energy. So let's calculate that. So we've got the energy. So someone actually do this. So I don't have a calculator. If you don't want to do it, we won't do it. We need to get the frequency. So we can put that energy, you don't can drop the negative sign. So it just becomes 4.084 times 10 to the minus 19 joules is equal to 6.62, I'll just say, times 10 to the minus 34, I believe it is, joule second, times nu. So if we divide that energy by Planck's constant, we'll get our frequency. .626. I put 6.62, which is good enough. Anybody do that?
6.16.
That sounds about right. That's hertz, or seconds to the minus 1. 6.16 times 10 to the 14 seconds to the minus 1. And now we're just going to do C equals lambda nu. So we got 3.0 times, whoops. Times 10 to the 8th meters per second. So I'm just doing C equals lambda nu equals lambda times 6.16 times 10 to the 14th seconds to the minus 1. That says 14. Isn't that terrible? Someone do that for me, please. 3.0 times 10 to the 8th divided by 6.16 10 minus 14. 10 to the minus 14. Good idea if you do these in class, you catch your mistakes, you learn how to do them, not wait to the exam or the quiz or whatever. You do that right? Oh, not negative 14, it's positive 14. Why did I put a negative there? That's not a negative. What Houston told me was correct. It's right over there. 10 to the 14, not negative 14.
4.87.
That's about right, yeah. 4.87 times 10 to the minus 7, that'll be meters, times 10 to the 9 nanometers per meter. That'll give us 487 nanometers, right? This is supposed to be the 4 to 2 transition, right? Let's take a look at where 487 nanometers is. And that's this one right here, right? They have it as blue, so 487, whatever that is. I wonder what that looks like in the, let's go back to the, there it is there. So 487, kind of like a bluish, maybe got a little green, heading into the green. Maybe that's why they wrote it as green there, just to distinguish it, but there are really 3 of them that are almost blue. And one's red. Got one that's kind of like a violety blue, then a dark blue and a lighter blue heading into green and a red. So that's the one we just calculated there, the 487. Questions? Yes, I'm sorry. I didn't change to a positive. That is the answer. It's going to be positive. So you need this here.
When we did the energy, we got a negative. We got a negative 4.084, and then when we went to.
Oh, well, as I said, the sign is just for absorption and emission. There's no such thing as negative energy. So you just drop the sign when you do your calculations after that. That's right.
And then the last part when we were getting the wavelength, and you were changing. And we got the 487 to the -7. We just did unit conversion to get negative.
Right. That's all. That's right. So we have 4.87 times 10 to the -7 meters. And then multiply that by 10 to the 9 nanometers per meter, get you 487 nanometers. And the negative sign you can drop when you go into Planck's constant. Question.
So with the speed of light, if you multiply by the 6.1 with the 6.16, did you divide?
So I have the speed of light's going to go in. Speed of light goes in here, and the frequency goes in here. So it's going to be speed of light divided by the frequency to get the wavelength. So there's the speed of light, and I had wavelength times the frequency, so I divide to get the lambda. Yeah, so 3 times 10 to the 8th divided by 6.16 times 10 to the 14, not negative 14. I changed that. I made a mistake. It's 14, not negative 14.
Oh, wait,
3 times 10 to the 8th divided by 6.10 to 14. 6 point. You do good.
Oh, hold on. I'm not putting
Something to, because I think that's right. I mean, it looks like it's right in terms of the actual band that we see there, so it should be right. Hold on.
Okay, yes.
You got it? Okay. Other questions? Your brain's fried? Well, we'll end with something light and fun. Take a look at this picture and tell me, raise your hand and tell me what you see. Yes, what do you see? Is it an old lady or young lady? Younger, and she's looking, how's she looking? So profile. The young lady with the feather in her hat with a profile. Do you see the other one? Yes. There's no smoke. But you do see the mouth. There's an old lady also. Okay, so this is her this is her mouth. She's looking down like this. Her chin is in this black shaw. Right? This is her eye here. This is her nose. That's her nose. Show up already. God, the delay. That's her nose. She's like this. She's looking more at us, a little bit less profile, like this. But then there's the young lady. It looks like some of you will take a while to see both. Some of you maybe never. Some of you see right away. Some of you only see the old, the young, whatever. I don't know. But so why am I putting this picture up here? That's the question. Well, it's kind of meant to say that at this point, what we're realizing is that the electron has both particle and wave characteristics. That's the particle wave duality you hear about. And depending on how you look at it, how you observe it effectively will dictate to some extent how it behaves. Sounds kind of quirky and weird. We'll go into this more on Thursday. But there is this particle wave duality. And we know this to be the case because electrons, oh, I can't do that yet. Well, I have it right here. Electrons have wave characteristics. When you think about waves, you have to think about reflect, whatever that was. I do have a mouth guard, and I had surgery on Friday in my mouth, so I had this retainer thing in there. You have to think about reflection, refraction, and diffraction, right? Those are what waves do. they reflect off the surfaces, they diffract. You know, when you look at a straw in a glass of water and it looks like it's bent, that's refraction of light, right? Diffraction patterns. That's what waves do. Well, we have electron microscopes right in this building. Just like a light microscope, it has to have wave characteristics. Those top pictures are visible light, right? Microscopes, and they're not the same. I tried to find ones that were, comparable, if you will. And the bottom ones are electron microscopes. So much better resolution. You can see actual, this is a mosquito, and that's like I don't know if that's a cricket or katydid or something, but, and then you got red blood cells. You can actually see an individual cell with a ruptured artery, Why can we see so much better? Because the wavelength is directly related to resolution. The shorter the wavelength, the greater the resolution. So that tells you that the electron's wavelength is much smaller than visible light. And therefore, an electron microscope gives you much better resolution. Okay, and that's kind of advanced physics and explaining how resolution is tied to wavelength and all of that. But just trust me, the smaller the wavelength, the greater the resolution.